universities. The list is so long that we may need an hour to just go over all of it. But maybe an interesting one is the NASA Langley Research Center at Hampton in US. He has published many interesting works in the area of control and optimization that are published in the top tier journals. He is also a fellow of International Federation of Automatic Control, as well as IEEE, and his research is in the area of data-driven optimization, stochastic optimization, and probability theory. So it's an honor having you here, Marco. And without further ado, I want to give the control to you.
Yes, thank you so much, Madrisa, for this introduction, and thank you so much for this invitation. And I would like to thank the whole organization, also Yannis in particular. And I would like to say that it's a great pleasure for me to be with you this afternoon and sharing this topic of mine with you. So let me go straight to the topic, which is data-driven robust optimization. So, robust optimization is pretty much the topic of this series. And what characterizes my own presentation here is data-driven. So the focus will be really on data-driven robust optimization. Should mention also that this is joint work with Simone Garatti and Dalgo Cray, and with Simone and Dalgo, we have had more than 20 years of strong collaboration, very fruitful and absolutely extremely enjoyable. So let me get started with some sentences here. The first is that robust optimization deals with the optimizing in the presence of uncertainty. And when it comes to uncertainty, there are mainly two ways to describe it. One is by using a bare set, which we call uncertainty set. The second one is based on endowing this uncertainty set with a probability distribution. I won't try to convey my own interpretation of what this probability distribution represents here, because this would stray us too much afield. But for the time being, I'll just say that let's take the probability distribution as a descriptor of the chance of happening. So in some problems, it turns out that we can really find a solution through optimization that works fine for all cases in the uncertainty set. But at least that's my experience. In many other applications, this is not the case, and the situation is more the one on the right. So in the left side, you see this azure color, which signifies that the decision is good for all possible occurrences of uncertainty. On the right, you see that there is this red portion, which signifies that the decision and the solution is not quite good there. And in my own life, I've seen many applications where the situation is on the one on the right. Let me give you just a very simple example. When we dimension a network for mobile communication, we never think of the worst. So the uncertainty set may contain things like one person at a time picks up the phone and make a phone call, or 10 people, or 100, or all of them. And no one dimensions a mobile network to cover the latter case. So basically, there is a red portion of the uncertainty set where things are not working properly, and under those circumstances, I see that we need to be quantitative. We need to have a tool to measure the extension of the red set. And to me, when this measure refers to the chance of happening, we call it a probability measure. So, but while this is true, the fundamental question pops up either ways. Whether you pick a description on the left or the one on the right, the question is who gives us the description of uncertainty? And in the era of data are often used as a first-hand source of information to describe uncertainty. So, in other words, we are more and more leaving the classical setup where the description of uncertainty is a datum of the problem. Say it is assigned and we start from there. More and more, we work with the complex problems where instead of starting from the idea that uncertainty is given to us, we should rather rely on various sources of information, and the data referring to the problem at hand is certainly a very fundamental source of information in modern problems. So there is I will say, a paradigm shift that we are looking at in modern robust optimization. And this era of data comes with new challenges. And here I identify what I believe are the two more important challenges. The first is indirect or direct. Indirect means that I do have data and I use them to first construct description of uncertainty. And from there, I move to optimization along the standard, the classical way. Once I have a description, I'm back to the normal path. Instead, in contrast, direct means that we have data and we go directly into the domain for optimization and we use the data there. We don't even try to reconstruct uncertainty before we optimize. So big challenge, should we go indirect or direct? And in turn, there is this second challenge, the dual role of data. So as long as I'm given a description of uncertainty, this is what I'm after, somehow accommodate that uncertainty set. But when I start off with data, data provides to me just a partial view on uncertainty. And therefore, there is a generalization issue that pops up naturally. So if I'm robust with respect to my data points, how does that generalize to new cases? Those that I have not seen yet, and those that I will confront with tomorrow when I will go to apply my design. So this is a fundamental generalization issue, which refers to the dual role of data. Data should be used on the one hand to make the design through optimization, but on the other hand, we would like to come up with the guarantees. We would like to guarantee that our result will work properly on a new as yet unseen case, the one that we will meet tomorrow when we will be applying our design. So in this talk, I will try to put forward my vision on these challenges, the challenges of the new world, and then I will move to present scenario optimization as a general tool to address these challenges. So let me start with the two challenges, actually with the first, indirect or direct. When preparing this talk, I thought the best way to answer this question or to address this question was by means of a couple of examples. And this is the first one, portfolio optimization. And I believe that we all know, but let me recap briefly what portfolio optimization is about. Say that I have in front of me the assets for investments, and the PK here is the percentage of capital invested on asset K. So I'm going to split my capital on different assets, and the PK is the amount I put on asset K. So I group together the pKs in a vector theta, and the theta, therefore, is the optimization variable. Then I have this formula. What's that? So RK here is called rate of return. It's defined as the closing price minus the opening price divided by the opening price. So it's either positive or negative, depending whether the price in the market goes up or down. And the RK is uncertain. Why is that? Because the market evolves in a way that is not completely predictable. And I group together the RKs in delta. Delta is, throughout my presentation, the uncertainty parameter. So here I multiply pk times rk. This is the profit, either positive or negative, I make on investing 1 unit of money on asset K. Then I sum over K. This is called the return of the portfolio. And this is a function of the two fundamental variables, theta, which is the optimization variable, the one I would like to choose, and delta, which describes the evolution of the market. Now, take this problem. I would like to select my theta, and I do have data. What are data in this case are performances of different assets in the market that have been experienced yesterday, the day before yesterday, and so on. So performances experienced in the past. What do we want to do with this data? How do we use the data to come up with a good solution when I try to maximize my profit here? So let me tell you a bit of a story that dates back at least 10 years now. I remember some 10 years ago, I was visiting Imperial College, and I had a very good chat with Mark Davis. Mark was an expert in finance and also in control, which is my original field, by the way. And I was talking with him about how data should best be used in this context. And I remember Mark told me, do you trust Black and Scholes equations? I said, yes. Then you must recognize that market prices follow a log normal distribution. Because, I mean, this is the solution of Black and Scholes equations. Then go pick your data points and estimate the parameters of the log normal distribution, which makes a lot of sense to me. But let's go through just a quick and dirty calculation here. So say that I have 100 assets, which, by the way, in no way is a large amount of assets. At times we set up portfolios with the 200s, 300s, 500s. So 100 is not extreme at all. If you compute the number of parameters in the log normal distribution, this goes up to 5,150. So say that we are after a daily investment. So I can look back in the past. In the market, in the stock market, normally there are something like in the order of 250 trading days per year. So if you want to collect 1,000 data points, you need to go back for years. And there is a general consensus that moving beyond this is really a stretch, because the market 4 years ago was following rules and distributions that really did not compare with the current condition. So basically, at the end of the day, you would like to estimate 5,000 plus parameters with 1,000 data points. So the first remark I'd like to make here is that in some applications, we simply do not have enough data points to even try to estimate reliably the uncertainty, a descriptor of the uncertainty. But there is more than that. There are good reasons why in many applications we do not want to pursue that objective. And this is explained in my second application here. That's a defibrillation, an application I've been working on for some 10 years now. So it has to do with the ventricular fibrillation. Let me just give you a bit of, the background knowledge. So ventricular fibrillation is the condition in which the heart has lost its systolic rhythm. So there is still a lot of electrical activity remaining, but there is no spontaneous circulation. So the electrical activity has become disorganized. So, and the heart doesn't work any longer as a pump. There is no circulation. So in that condition, a patient dies in 7-8 minutes. In half the time, the brain gets destroyed by lack of oxygen. Now, it happens that all guidelines in the world, well, I know well the European guidelines, but all guidelines in the world prescribe that if a defibrillator is available, it should be immediately taken, and the electrodes must be placed on the patient's chest, and the patient must be shocked. So an electrical shock goes from the device to the patient. And electrical shock is a reset signal in the hope that the systolic rhythm will be restored. It's important for you to know that this happens at the first shock only in 20% of the cases. 20%. And should you know that the shock will be ineffective, you should not shock. Because there is medical evidence that an ineffective electrical shock further damages the cardiac muscle. And secondly, there are alternatives. It's very well known that a properly given cardiac massage before shocking really boosts the chance that the shock will be effective. So the big challenge in this field is, as given by this goal here, predict whether the defibrillator shock will be effective. And you need to know that any modern defibrillator can do two things. One is shocking from the device to the patient, but the other thing that the defibrillator does is collecting a short ECG, electrocardiographic tracing, of the remaining electrical activity in the patient's heart, and this is sent to the device. So the idea is to build in the device a classifier that receives as input the short ECG and provides green light, shock now, the shock will be effective, or red light, don't shock now, the shock will be ineffective. So this is a huge, an enormous medical problem and a big challenge. And of course, here the problem is to optimize. So we want to minimize the chance of misclassifying the patient. Now, what is a data point in this context? The data point is a couple UI, where U is an ECG. That's a typical ECG of a heart in ventricular fibrillation, and the Y is 01, ineffective or effective shock. Now, you take a look at this data point, and the first thing that jumps to me is that, this is a very complex U, because it's an infinite dimensional object. It's a waveform. People do not work at this level. what they do is that they first extract features either in time domain or in frequency domain. And what is used in this medical application are 9 features. At times they use 4 features out of 9, at times 3, at times 2. Let me go to the extreme low, 2 features. Now, if we want to use the data to reconstruct a uncertainty, to construct a description of uncertainty, we are after this. So this is level 0, unaffected shock, level 1. This is the first feature, and this is the second feature, and this is how the population distributes. So my goal, if I use data to reconstruct or to construct a description of uncertainty, I'm after constructing a descriptor of this, which is a formidable task in itself. You can think of how difficult it may become when you scale up to 3 features, 4 features. But there is an observation which matters here. Let me shift the level 1 down to level 0. What I'm really after in this application is this gray object. This is called the bias. Oops, sorry, there are these spikes, but the bias classifier. So the bias classifier is as simple as this. It says 1 where red outdoes blue, and it says 0 where blue outdoes red. And provably, and that's an easy fact, this is the classifier that minimizes the risk of misclassification. And the sheer fact here is that this object is way simpler than the distribution of the population. So basically, if we go the indirect way, we are trying to solve first a more difficult problem to come up with the solution of a simpler problem. So just to summarize this first, that's my experience. For simple problems, the indirect path works well. However, as the complexity of the problem increases, the indirect path falls short. And I believe that this will become more and more truth alongside the technological advancements. Therefore, in real problems, it may be convenient to aim for a direct path from data to optimization and guarantees. Let me come to the second point, certified data-driven optimization. And my first claim here is we should aim to develop a science for data-driven design. And the emphasis here is on this word, which is science. What do I mean by that? I'm not happy enough just to have an algorithm that crunches data to come up with a solution. That's not enough. So in order to say that we have a science for data-driven design to optimization, we need also to have certificates, to have a theoretical approach that endows the method with the guarantees. And I believe that we all agree with this claim. When I tell people this thing, often I receive a return the comment, then you have to use priors. How can you guarantee what you do based on data without having priors? Let me comment on this point here. So by way of just a simple conceptual example, say that I have 2 data points here and here. This is input, and this is output. I had 2 data points, just a conceptual example. And next, I'm given the input of 1/3 point, and I'm asked, where is the point going to be? I may want to make this construction. I connect the 2 points, and I lift my blue dot until I hit the connecting line. And then I would like somehow to certify the quality of this construction. And this quite naturally prompts me to saying, okay, but you need to use a prior for that. So the question is, how do we know that a connecting line is a good construction? Are we perhaps assuming that the underlying phenomenon is somehow linear? And by the way, when telling you this story, it makes a lot of sense to me as well. However, should we aim higher? And by this, I mean exactly the following. I want to use prior knowledge and data to make a design. Of course, prior knowledge, domain knowledge is very important. When I set up any optimization program, I want to use prior knowledge. Once the design has been made, I'm left with a design and a value based on data, and I can look at it, and this becomes available to me. However, when it comes to guarantees, really guarantees refer to something I have not seen yet, to the future, to an out-of-sample case. And this is not something that I can inspect, even a posteriori. Therefore, I would like that my guarantees are only based on data. I don't want the prior to have any role there. I want my guarantees to maintain intact their validity even when the prior fails to be correct. I'll come back to this later. So the question, of course, is this at all possible? Is this at all possible? So let me recap this first part. In this first part, I've tried to put forward my vision. My vision is, in many cases, indirect, may fall short, and possibly in many applications, going the direct way from data to optimization has a better chance to work well. And the second is that we need not be happy with just putting forward algorithms. We also want to put forward guarantee certificates to create the new framework, the new theoretical framework for data-driven, robust optimization. And now let me come to the scenario optimization, an eminently direct approach with guarantees. By the way, the scenario optimization is a body of methods. So it contains many different methods. When preparing this talk, I decided to stay concrete. So I'm going to present mainly two algorithms. There is more, but I will stay concrete. So my first setup is a data-driven, robust optimization. So it goes like this. These are my data points. So throughout the remaining of my talk, delta 1, delta 2, delta n is the sample of observations I have. In this theory, these are also called scenarios. So scenario is same as data point or observation. And these are independent from a distribution P. P is not something that I know. I can have partial knowledge of P, no knowledge of P, so my wealth comes from the data point. And this is the program I want to solve in a data-driven robust optimization setup. I minimize the cost CX based on constraints as given by my data points. In the next slide, I'll provide you with one example. Then I have this notion of risk. What's the risk? Is the probability with which one next point that I will experience tomorrow will be such that my solution to this problem will be in violation of the corresponding constraint. Depending on the application at hand, this may mean a number of different things. In a control application, this constraint may refer to stability. So my design doesn't satisfy stability constraints. In an investment, this may mean that I'm in a shortfall condition. In a classification problem, this may mean that I misclassify a certain example. But let me give you an example of this setup, just one example. Say that you want to minimize J theta delta. So think of portfolio optimization. Well, in portfolio, you want to maximize. So here is just minimization, place a minus in front. So you are given data points. What you can do is that you can plug the data points into your J function here. And now this is the first function, the second, third. Oh, by the way, all my drawing are flat, but think of this theta as a multidimensional object. Then say that for some reason, I want to do a worst case optimization, which amounts to say, okay, I first take the maximum of J, which gives me this top surface, and then I minimize with respect to theta. And that way I find my design theta star and the corresponding value. That's an empirical value based on data. Of course, the first thing I will do is to inspect this value. So say that this value is 2.72 and say that this is a good value for me. So I'm happy with that. Should I then use theta star? Again, that's a problem about generalization. This is a value I have experienced on the data set I have. So first, let me recast this problem in the setup that we had on the previous slide. This, of course, can be done by epigraphic reformulation. I optimize over X, theta J, I optimize J, so I minimize in this direction under the constraint that J is above each single function. So this is not allowed, this is not allowed, this is not allowed. And of course, I found this point, theta star and J star. And now we are within our setup, because if you go back, you are exactly within this setup here. You minimize the cost with the constraints as given by scenarios. Then let's ask, what's the risk for this example? The risk is the probability that tomorrow I will encounter a delta such that corresponding to my solution, I am in violation of the constraint. So bigger than or equal to is not satisfied, so the other way around is correct. This corresponds to seeing a situation like this one, where for the new delta, the incurred loss is higher than J star. So basically, risk in this application means I'm incurring a loss higher than what I have seen at the time I have optimized. Again, the concept of risk is very diverse depending on the application. May mean probability of destabilizing a loop in a control problem, can be the probability of mispredicting in a prediction problem, and so on and so forth. So back to our problem here. So this, as you can see, is a direct method for optimization because I'm directly using my data points in the optimization domain, and then I ask for the risk. Question, can we certify the risk? And today I would like to talk to you of a beautiful marriage between two fundamental concepts. One is risk, the other one is complexity. So by now you know what risk means. Let me talk to you of complexity. What is complexity? So let me start with this example we have seen already. The idea is that if you remove the scenario corresponding to this function, the solution drops. Same on the other side. So complexity is 2. If only 2 delta I are maintained, the solution doesn't change. The concept of complexity is very general. Let me give you another example. In this example, I have 500 points on R2 generated by an unknown probability distribution, and my construction is I construct the convex hull of the points. And I use this, say, for prediction purposes. So I predict one next point to be outside the convex hull. So the risk in this case is the probability that the next point will be outside the convex hull. In this case, if you count them, I have 7 points at the boundary. And this is the complexity. Why? Because the convex hull is built using the following optimization program, the one here. So you minimize the volume of set S, and S is any convex set on R2 under the constraint that each single point is in the set. Oh, by the way, this gives me the chance to say that this setup is very general, because if you take a look at it, this is not a finite dimensional optimization problem. So let me go back a second to our setup, this one here. There is no assumption that X belongs to a finite dimensional vector space, nor there is the assumption that it belongs to a vector space. Can be finite dimensional, infinite dimensional, and beyond that can be any set. So it's a very broad framework. And it contains in particular this problem here. It's just a particular case. Then you start dropping one by one all the scenarios, but the 7 at the boundary. And you observe if only 7 points are maintained up against the same solution. So complexity is 7 in this case. So complexity refers to a compression. You want to compress the initial set into a small one so as to preserve the solution. Now, intuitively, low complexity should imply low risk. Let me tell you this story about even another example I ran some 10 years ago together with Simone Garatti. So let me explain this example. I'm going to use my hands for that. So do you see me? So you see me, no? So say that I generate points in R3 in the space. Points there. Then I consider the negative octant. So that's the region, negative axis, negative axis, negative axis, and I optimize by pushing towards the negative directions my octant as much as I can, while keeping all the points inside the octant. So it's very similar in spirit to the convex hull. So there are points in the domain, and I optimize. Now, what I did with Simone was I made this construction in 400 dimensions, not 3, 400. So in 3 dimensions, you can see that complexity corresponds to the points that are at the boundary, and they prevent me from further improving. So I can have 3 points at the boundary, 1, 2, 3, or just 1 at the vertex. In 400 dimensions, everything can happen. Complexity fluctuates depending on their realization all the way from 0 to 400. So what, if you look at the slide now, this is the bivariate distribution for this example of complexity and the risk. And you can see that the complexity goes all the way from very small to 400. Importantly, the risk is something that we cannot measure because depend on the generative model of data, something we do not have in a real application. Instead, complexity is something that we can measure. It's an observable. A statistician would call it a statistic of the data points. This has only to do with the optimization domain based on data. This is something I can measure. Then you take a look at this bivariate distribution and you say, hey, but there is a lot of correlation between risk and complexity. So much so that I can measure complexity and estimate the risk. So if I measure 250, I can say, okay, risk will be here. If I measure 150, I can say, hey, my risk will be in there. Now, there is a very deep question is, how general is this result? That's just one single example, but how general is it? Answer, this result is universal. Complexity and risk go hand in hand always. So let me explain this with a theorem. So this is again our setup, and this is the theorem. Suppose only one irreducible support set. This is the only assumption here, which means that the observations giving us the solution is just one single group. This, for example, in the convex hull example, rules out the possibility that 2 points are one on top of the other in the same location, so that you can replace one with the other. Then risk is in sandwich between two functions of the complexity. I'm not going to explain this in detail now because I want to explain this in the next slide with a graph visually. What I want to do now is to tell you that you can even drop. You can doesn't work anymore. Why? Okay, you can even drop the only assumption here, and you have to give up with a lower bound, but the upper bound, which is the important one, because your bounded risk is still valid. And what this result says is on display here. So in the complexity risk domain, there is this elongated region, this one here. And the claim is, independently of all circumstances, in particular how data have been generated, the bivariate distribution of complexity and risk has to lie in this region all the time, so that we can accurately estimate the risk from complexity. Not quite, it's not completely true. There is a small leakage outside, and this is called confidence. Confidence can be set to 10 minus 4, 10 to the minus 6, 10 to minus 8. And you may see in your monitor that, in fact, there are 3 nested elongated regions. So when you go down from 10 to the minus 4, 10 to the minus 6, 10 to the minus 8, you have just to very gently enlarge your elongated region. to me, 10 to the minus 8 is a zero for any practical purpose. And this holds true totally distribution free. Totally distribution free. So let me go back to the orthant example. I have added for you here the elongated region. So you see that distribution is within the elongated region. There is no claim here that the distribution is all the time the same. The distribution is much changeable with the generative model. So with Simone, I run the same, exactly the same construction with another distribution in R to the power of 400, and this was the complexity risk distribution. So it's totally different. But for what matters here is that the distribution is all the time within the elongated region so that we can estimate very accurately risk from complexity. Then you start generalizing. So this was the completely robust scheme where you impose this constraint, then you rewrite this as a function less than or equal to 0, which without any loss of generality, and then you drop this requirement 0, you relax it. You allow f to be less than xci. Xci is bigger than or equal to 0, so if at optimum this is 0, you are satisfied the constraint. If not, you are in violation of the constraint, and you pay a penalty for this to happen. And this rho is an important tuning knob. When rho is set to a very large value, you are back to the robust setup, fully robust setup. When you decrease the value of rho, you start trading robustness and the constraint violation for performance. This setup is very much used in practice. It's everywhere. I'll just mention one single setup. If you look at SVM, support vector machine, it's exactly within this setup. And in here, you get exactly the same results as before. First, you define complexity, this time the following way. The number of Ci star at optimum bigger than 0. This is called the empirical violation. How many constraints you are violating corresponding to the solution. And then you add delta I, so many to give you the solution. By the way, you may raise your hand now and say, okay, but then you, Marco, have different notion of complexity depending on the scheme. Yes, that's true. Let me make a remark here, however. As said before, there is a more abstract level where there is only one notion of complexity. We are looking at the lower level of algorithms, robust, relaxed, and more. At this level, the notion of complexity splits, and we have different notions. But at the upper abstract level, there is only one notion of complexity. And then exactly the same result as before applies. Same result. So at the end of the day, all the time we do have this result linking risk and complexity. And now it's time to go back to my question, should we aim higher? So again, prior is very important when it comes to setting up the optimization program. Let me give you an example. I want to make an investment in the market, and I may know, or I may tend to believe, or I may just think that at this point of time, the automotive sector is more bull market than the pharmaceutical sector. So I go and place in my portfolio more assets from automotive. And then I balance my portfolio based on data. So this prior knowledge matters to me. It's important. I want to make the most of it. Then I make the design, I balance my portfolio, and I have an empirical return, something I can see the J star. However, when it comes to guarantees, I want to be fully guaranteed whether or not my prior that I was somehow using and I was not so sure about is or is not correct. The guarantees should maintain intact their validity, whether or not the prior is correct. So just repeating this, you make the design and you check for features of interest, and these always remain intact. All this, I believe, is very important to develop trust in the decision. So I've seen very often. I've done quite a bit of work, for example, in the use of renewables for energy production, and people are skeptical because there is a lot of uncertainty there. Should I bet on or bid to generate this much of electricity tomorrow? There is uncertainty in the weather forecast, these kind of things. Now you need to provide guarantees. To get people to develop trust in the decision they make using data. And the second also is that that's very important to tune hyperparameters, because if you look at the empirical result on the one hand, but also you get guarantees, you get the full picture, and therefore you can choose among alternatives. And just as a very small final contribution in this talk, let me give you an example of the tuning. This is called the SVR in the machine learning literature, support vector regression. And you have data points in the input output domain, and the goal is to construct a tube used for prediction. So given an input, you predict the output to be here. Now, this is again within our relaxed scheme. Gamma, what we optimize is the width of the tube. So of course, we like having a small tube because the prediction becomes more accurate. One constraint when you say 0 here means that a data point is inside the tube, but then you relax it. By the way, here you see 2000 data points. They look very dense, but because the picture is in one dimension, and you can think of a high dimensional space. I've also used a Gaussian kernel in this example, and the parameter I'd like to tune for you is rho, the tuning parameter to trade a better value of the cost, and you are ready to violate some of the constraints. So I run with this data set this problem for you, and this is what I found. So I tried the 15 values of rho. When rho is large, very large, I got this value. So this is the width of the tube. And as I started decreasing the value of rho, I went down this way. So for the second largest value of rho, I experienced this, then this, then this, then this, then this. This is something that is given by the optimization program, something we experience. We don't have in advance. And this is, again, the elongated region as given by the theory. So you get the full picture, cost versus risk. And in this application, I select this value of rho. The width of my tube is 0.3, which is good enough for me, while the risk was guaranteed to stay in this range, 0.030 to 0.08, which was good enough for me. And by the way, this was the construction I made. Just to let you know, if you go to this extreme, large rho, then the tube is large, very well guaranteed. This is a fully robust optimization. And if you go to the other extreme, the tube is very small, but actually you are guaranteed to have a high risk in this case. And this is what you construct. That's the fully robust construction. And this is the other way when you take a small role. Okay, so let me just wrap up with some conclusions. So we aim to develop a science for data-driven robust optimization. So data-driven is, to me, is very important. It's the future. In applications, we use data to optimize, but we want to be scientists, I would say. We want to have a theoretical approach, not just a crunch machine for the data. We would like to give guarantees. That is, we want to optimize based on data while also providing certificates that maintain intact their validity when the hypothesized prior fails to be fully correct. And then I presented the scenario approach, which is a body of direct data-driven optimization methods with distribution-free certificates. Among other things, I believe that these results show that data can well stand the dual role of provide information to optimize while also assessing the robustness of the ensuing result. Okay, so I would like to stop here.